Okay, we left off talking about why won't sine magnitude work efficiently in a computer, and I gave you 2 reasons. Remember those 2 reasons. I promise you, you'll hear that question again. So, if sine magnitude doesn't work, I peek over here and I say, okay, what's the next thing? Why or why not? Well, we know not, and we know the 2 reasons. So 2's complement representation. What the heck is 2's complement? I don't understand that at all. Well, not too bad. But let's go back. Before I even tell you 2's complement, you've heard 2's complement before in 2350, discrete structures. Imagine, if you will, that your grandmother has a stationary bicycle up in her attic. You bring it down because she's going to sell on a garage sale. You get on this stationary bicycle. Guys, it's a stationary bicycle. Its only purpose is to give you a little bit of exercise. So guess what? You don't need a back brake. It means you can pedal forward or you can pedal backward. Now, every one of these stationary bicycles has an old mechanical odometer. This old mechanical odometer, let's say the one on Grandma's bicycle, stationary bicycle, has 1, 2, 3, 4, 5 cylinders. Okay, oh gosh, that's a rotten drawing. Anyway, trying to do 3-dimensional, not doing so well. Not with a stylus anyway. I'll do a much better job in class. That means if I have 5 places here, I can represent anywhere from 0 to 99,999 on Grandma's bicycle, okay? But what happens if on my odometer, so let's say binary odometer, if I say 0, 0, 0, 0, 0, what is that? Well, that's 0, a decimal. And what is this? That's a 1. And what is this? Oh yeah, that's a 2. What if I get on the bicycle, the odometer's set to 0, and I pedal backwards? I'm going to bring to class just a little. These are each cylinders, but it's like taking a paper towel roll and cutting it, and then cutting each one of those cylinders, the smaller cylinders, so that I can unroll it into a large rectangular piece that, if I roll it back up, would be the cylinder. On this rectangular piece, it goes from 0 all the way to 9 at the bottom. Okay, so when I pedal forward, the cylinder is moving toward me. So 0 becomes a 1. If, however, I start at 0 and I pedal backwards, then the cylinder is moving away from me, or in that direction, which means a 9 is going to show up. Okay, so -1. If I pedal backwards 1 mile on my binary odometer, it will read 99999. If I pedal backward another mile, it'll be 99998. So, a couple of things you see from this. It's pretty counterintuitive. These numbers look like really large magnitude numbers, but we see that they're actually really rather small magnitude negative numbers. That's okay. I mean, I think we can get by with all of that. More importantly, though, let's find out if we will get the right answer. So let's go back to let me change the problem a little bit so we can play with it. Let's say we want to add 8 plus a -3. What should our answer be? Our answer should be 5. Okay, now let's convert these to binary odometer numbers. I get 0.0008. Negative 3. Guess what negative 3 is going to be? 99997. So I'm going to add 99997. Okay, 8 plus 7 is 15. Carry my 1. 1 plus 9 is 10. Carry my 1. And I go on and on and on. And here's the deal. My answer is this, but I've only got 5 cylinders to show my answer in. So it doesn't really matter. That's my answer. And guess what? It's the correct answer. So I now have a method of representing signed numbers that gives me a correct answer, and only one way of representing 0. So let's take this. Let me get rid of all of this stuff. Let's rewrite this so that we understand what this is going to look like, not only in binary odometer, but decimal, binary, and hex. Okay, so ... 210 minus 1, whoops, we'll go this way, ... 2. Here we go. 2, 1, 0, minus 1, minus 2, ... And we said this looks like 2, 1, 0, and then 99999, 99998. Okay, and so on. In binary, and I'm going to say 8-bit, just to minimize what we have to draw here. 8-bit. This is going to be it's going to look like that. I know, just a little tedious. But here's where we get to, remember, now we're dealing with a mechanical odometer that instead of going from 0 to 9 goes only 0 to 1. So instead of the cylinder rotating away, when it rotates toward me, now it's going to show all ones. And so on. Okay? Or if I look at this in 8-bit hex, 8 bits means I'm going to have 2 hex characters. Handy, this looks the same. Here, this looks like F, 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 E, and so on. Okay. Whew. Now that we've got this, let's play with it a little bit. Okay? We've talked a little bit about binary odometer numbers. We know that they work. Now we need to focus on how we start to get familiar with what binary odometer looks like in binary and hex. So let's do some examples. Before we do some examples, let me talk a little bit about the formula for 2's complement. Formula is shown here, where in this case I'm calculating the 2's complement of a value n, of n, small n, so of large n, sorry. The size, or the number of bytes, is small n. So, So here's the formula, the 2's complement formula of some value n. Okay? And you think, and you look at this, two things I want you to notice. First of all, I am subtracting a 1 here only to add it back later. This doesn't make any sense. So let me spend a little bit of time and explain why this is going to work. Okay? Again, let's think about binary odometer. 5 decimal places. That means I've got 10 to the 5th, which is a 1 followed by 5 zeros. Well, guess what? That's 6 decimal characters, and I only have 5 places to show. So if I subtract 1 from that, I'm going to get, well, I'm going to borrow a lot, and so on. Wow, this is tedious, but that's okay. I'll do it one time. So 10 minus 1 is 9, 9 minus 0, and so on. Oh, guess what? If I take 10 to the 5th, where little n is my size, and subtract 1, I get something that fits in 5 places. Then I'll subtract my value from that. So let's say we're trying to calculate the 2's complement of positive 32. And I subtract 32 from that. And then all I have to do to make sure I do this right is add the 1 back in at the end. Okay? So let's apply this. Instead of binary numbers, let's take this back and say, okay, I actually am just interested in binary or hex, doesn't matter. And here's the deal with 2's complement format. The 2's complement format is my method for showing sign numbers, or numbers that can be either positive or negative. Positive values are easy. I'm just going to convert those. We saw that in our previous slides, where positive 2 in decimal equals 2 in hex. That's easy. So we just do the straight conversion. So where it gets tricky is when I want to see what a negative value looks like in 2's complement representation. Remember, those negative values, it's hard to tell what they look like because it's a little counterintuitive. In fact, it's opposite what we would assume. Larger magnitude means smaller negative value. So let's say I want to find out what negative 32 looks like. So minus 32, what does that look like? And again, here I have to tell you what fixed length I'm going to use. And we'll say 8-bit 2's complement. Okay? Here's what I'm going to do. If I calculate the 2's complement of positive 32, if I use this formula on positive 32, then I'm going to see what negative 32 looks like. Okay? So that's what we're going to do. So let's walk through this. 2 to the n, 2 to the 8th minus 1. And we'll do this in hex first. In fact, guys, I'm going to do most everything in hex. They're an order of 4 fewer mistakes that can be made in every iteration, every mathematical operation that you do. So 2 to the n minus 1 in hex is going to be FF, and I'm going to then subtract n, so n is 32. Ooh, no, it's not. That is decimal. What does 32 equal? 32 decimal equals 20 hex. Okay, so I need to do this in the same numbering system. So F minus 0 is F, F minus 2 is D. Now, I don't want to forget to add 1. When I add 1, and let's just do this over here, df plus 0, 1. 15 plus 1 gives me 16, or 1 carry my power of 16. 1 plus d equals E. So guess what? Negative 32 as an 8-bit 2's complement number equals E0. Okay? All right, something I want to show you that's just kind of interesting about this. When we do the 2's complement formula, always nice, always works. But there's one thing I want you to notice. Let's go back to the problem we were just doing. And let's say, yeah, so we said negative 32. We said that was E0 hex as an 8-bit 2's complement value. Okay, or, well, 2's complement, that works. When we did this, we did 2n minus 1, which is FF, minus n, FF, minus 20 hex, and I got DF, and then I added 1 back, DF plus 1, we said that's E0. Okay? One thing I want you to notice, if I write out 32 in binary as an 8-bit number, I'm going to get this. If I rewrite this value, let me change colors just to highlight. Maybe now we'll go with we'll do red. So if I were to rewrite DF, or my result after this step, I would get 1, 1, 0, 1, 1, 1, 1, 1. You'll notice the difference between this number and this number is every bit has been flipped. When we have that, we have 1's complement. So the 1's complement of 32 looks like this. The reason I tell you that is a lot of people will prefer to do these problems in binary simply because of this. I still find it a little excessive. Let me just show you why. Again, let's say now it's going to be 16-bit 2's complement. And I say 2 to the n minus 1. 2 to the 16 is a very large number, 65,500 and, oh my gosh, 76, something like that. 60, yeah, something huge. And I'm going to subtract from that n. When I subtract 1, however, I get something really nice. And it happens to be all 4 F's, which in binary looks like this. So there's that part. When I subtract 1, we're still going to do minus 32. We're just looking at it as a 16-bit number, not an 8-bit. So I'm going to subtract 32. Well, we said 32 equals 20, but that was when I had an 8-bit number. 20 is still there, but now it's a 16-bit value. Guys, here's a critical note. when you're converting from decimal to 2's complement, always make sure you convert first to the correct fixed length. If you don't, you're taking a big chance that you're going to get a wrong value. Okay? So positive 32 looks like 0020 hex. We're going to subtract that 0020. And when we do that, 1111, 1011, 1111, 1111. Okay? Then I lost a 1 over here. So, again, I remember that this was DF. Well, now this is FF, DF. Okay? So if I just say 32 looks like that, which is let's write it out in binary. If I flip the bits, then the 1's complement of 32 looks like, and I'm merely flipping the bits in the original value. Okay? That gave me the same thing. All I have to do to this is add the 1, because remember, flipping the bits is the equivalent of doing this portion of the problem. If I add 1 to it, in this case, 1 plus 1 is 1, 0, or 0, carry my 1, 0, carry my 1, 1, 1, 1. Let's keep this going. 0, 1. 1, 1, and that's our answer, okay? Or, in hex, this would be F, F, E, 0, which is exactly what we found before, except this time it's in a 16-bit fixed length. All right, guys, let's stop it there. We'll pick this up again next time.